What's going on, Algebra Bros? In this video, I'm going to discuss the rational zeros theorem and show an application of it. So the rational zeros theorem is, I would say, an underrated result in algebra. And let me explain why. One way of trying to figure out what the real zeros of a polynomial function is to plug in different values for x and see if any of them give you an output of 0. Now, how many numbers could we plug into a polynomial function? Well, if you think about the domain of any polynomial function is all real numbers. Unless, of course, you're working in an application setting where there might be some domain restrictions. But in general, the domain is all real numbers. So if you go with a sort of guess and check approach, you've got infinitely many numbers that you can check and see whether or not any of those that you plug in are real zeros. You can imagine how time-consuming that would be, and as well as frustrating. The rational zeros theorem really helps us to focus in on what numbers could potentially be rational zeros. And by the way, it's called rational zeros theorem because this only applies to potential zeros that are fractions in format, or integers and whole numbers. This does not help us with any irrational zeros, such as the square root of 5 or 1 plus the square root of 3, but it gives us a start. So, with regard to the rational zeros theorem, it says that every rational zero of a polynomial function, regardless of how chaotic it may look, is of the format plus or minus p over q. Now p is going to be a factor or number that divides a sub 0. And q, the denominator portion of it, is a factor of the leading coefficient a sub n. By the way, I will sometimes refer to this as the p over q method. I think it might be obvious as to why, and that's because of the format of our possible rational zeros. Now, it's important to note this lingo here, p is a factor of a sub 0 and q is a factor of a sub n. That basically means divisor. Okay, so p is a divisor of a sub 0 and q is also a divisor of a sub n. So here's why I think it's underrated, because we have infinitely many numbers that could possibly be zeros without knowledge of the rational zeros theorem, but with the knowledge of the rational zeros theorem, it greatly narrows our focus as to which of those real numbers, particularly those that can be written as a fraction, are potential zeros. So this significantly reduces the amount of guessing checking we would normally have to do. So as an application of this, we have an example where it says list the potential rational zeros of the polynomial function, then use the graph of the polynomial function to guess what one of the zeros is. Check your guess using synthetic division. So let's first start with the list of rational zeros. The numerator of the fractions are going to be built out of divisors of 5. So I'm going to make a list for p, and I'm going to include both positive and negative numbers that divide 5, which would include plus or minus 1 and plus or minus 5. The denominators will be built by using divisors of 3, which is where our list for q is going to come from, and positive and negative numbers that divide 3 are plus or minus 1 and plus or minus 3. Now as for p over q, what we're going to do is treat each one of these numbers in the list for p as numerators, and each number in the list for q as denominators. And what I normally do is I go from left to right in the list for p, starting with 1, and I'll set it on top of 1, and then my other fraction will be on top of, or will be made out of 1 over 3. You really only need to use one copy of the plus or minus symbol. So my first fraction is plus or minus 1 over 1, or if you want to write that as plus or minus 1, that's fine. My second fraction will be plus or minus 1 over 3. And I've exhausted all denominators for the p-value of 1. Now I'm going to do the same thing with the p-value of 5. In other words, 5 as the numerator. And I'll get two fractions that way, plus or minus 5 over 1 and plus or minus 5 over 3. Of course, you might get values of p and q where things simplify, and there's also a potential to get duplicates in your list, in which case any duplicates can be discarded. Alright, we don't have any duplicates here. We could simplify if we wanted, to write 1 over 1 is 1 and 5 over 1 is 5, but I'm going to leave it as is. So that is our list of the potential rational zeros. And so we've gone from infinitely many possibilities to 2, 4, 6, 8. Alright, that's the power of the rational zeros theorem. Now, for the next part, we want to graph this polynomial function. So in our graphing calculators in y1, we're going to enter in 3x cubed minus x squared minus 15x plus 5. So let's do that. I'll do zoom 6. Alright, I'm going to sketch this graph out and then I'll come back to the graphing calculator. So just a rough sketch here. That's y1. And as you can see on the graph, there are 3 x-intercepts. And what that means is that this polynomial would have 3 real zeros. And if you think about it, our list for p over q has 8 fractions in it. So not all of those could be zeros, which is why you'll always see list of potential rational zeros. And there are some cases where we might get all of our zeros from this list. We might get just a couple, maybe one, or in some cases we don't get any numbers from the list as zeros. So to figure out, what could possibly be a zero from that list, you want to just kind of eyeball where this graph is crossing the x-axis. Maybe you're thinking it crosses at -2. Looks like it's crossing at some place between 0 and 1, and then perhaps +2, although it looks like it's just a little bit past it. So you want to just guess as to where the graph is crossing the x-axis. And now let's say that we think it crosses the x-axis at -2. So this is a guess. If we think that the graph crosses at -2, then if it truly does cross at -2, then -2 would be a real zero. Now we're not sure unless we put it to the test. And what I mean by that is we're going to do synthetic division with -2 and see if we get a remainder of 0. Now these numbers right here come from the polynomial f of x. And let's do synthetic division. -7, 14, -1, and then 2. So if you look at the remainder of when we do synthetic division with our guess, we get a remainder of 7, which if negative 2 were in fact a real 0, 7 should be the number 0 instead, but it's not. Therefore, negative 2 is a bad guess on my end. Or in other words, you gotta try something else, okay? So maybe it crosses at positive 2. Let's see about that. We'll put it to the test with synthetic division. Use the same numbers to the right. Alright, we'll breeze past this. And this gives us a remainder of negative 5. So 2 is not an x-intercept, nor is it a real 0. We have one more shot at this. We want to guess a number that's between 0 and 1. Now, something we haven't been doing with our guesses is checking to see if these numbers would be from our list of P over Q. After all, negative 2 and positive 2 are rational numbers, so the rational zero theorem says that if there are any rational numbers, they're only going to come from this list. Now, if you notice, negative 2 and positive 2 are nowhere to be seen in this list. So checking them, if we knew that in advance, there would actually be no need to even check them with synthetic division. Alright, but I wanted to do it anyway, just to show you how to guess and check. So let's approach our guess with, let's make a better informed guess. I guess I'll say it that way. So this third x-intercept, or the middle one, looks like it falls between 0 and 1. Now there happens to be a number in this list that's between 0 and 1, and that would be 1/3. So maybe, just maybe, 1/3 would give us a remainder of 0. So let's see about that. And I'm actually going to get rid of that just to free up some space. Although we don't do it a whole lot, it is possible to perform synthetic division with a fraction. Okay, the process is the same. Bring down the 3. Now, you gotta love this. 1/3 times 3 gives us 1. And when you add negative 1 to 1, you get 0. So 1/3 times 0 will give us 0. And you gotta love this too. 1/3 times negative 15 gives us negative 5. And boom shakalaka. 1/3 is actually one of the true real zeros for this polynomial function. So based on that, we'll say 1/3 is a real 0. So that's how you guess and check. Alright, so to recap, first make your list of potential rational zeros, graph your function, try to eyeball where the x-intercepts are at, and maybe cross-reference where you think the graph is crossing at, or touching, with your list for P over Q. Okay? Like we saw with negative 2 and positive 2, we probably shouldn't even have bothered with synthetic division with those two numbers because they don't show up in this list for P over Q. Alright, but when we looked at the intercept between 0 and 1, you know, a good guess for a fraction should come from our list. And so 1/3 happens to fall between 0 and 1, so it would make sense to check that number, and lo and behold, positive 1/3 gave us a remainder of 0. Okay, so long story short, make your list, graph your function, and then cross-reference the intercepts that you're eyeballing with your list for P over Q to make an educated guess. Alright, let me know if you have any questions about all that. Otherwise, I'll see you in the next video.